NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Wow, we packed the house tonight. How's everybody doing? Excellent. Well, thank you all very much for, again, coming to attend these wonderful lectures. We very much appreciate them. The Cassini mission, a cooperative undertaking by NASA and the European and Italian space agencies, has revolutionized our understanding of Saturn, its rings and amazing assortment of moons, and the planet's dynamic magnetic environment. The astonishing discoveries continue to this day, and we can't wait to see what happens when Cassini repeatedly dives between the innermost ring and the top of Saturn's atmosphere during its final 6 months, starting in April 2017, before finally plunging into Saturn's atmosphere in September. Tonight, we have two guests who will present highlights, expectations, challenges, and the promise of Cassini's final year. Dr. Earl Mays is the manager of the Cassini program. A veteran of 32 years at JPL, he began his career working on the navigation and engineering teams for the Galileo mission to Jupiter. After Galileo's final Earth flyby, he transferred to Cassini as the spacecraft operations manager and then deputy project manager. He left the project for 8 years to hold management positions in guidance, navigation, and control in avionics, then returned to Cassini as the program manager in January 2013. Dr. Linda Spilker is the Cassini project scientist and a co-investigator on the Cassini Composite Infrared Spectrometer team and has worked on Cassini since 1988. Since joining JPL almost 40 years ago, her first and only out-of-college job, by the way, she has worked on the Voyager project, the Cassini project, and conducted independent research on the origin and evolution of planetary ring systems. She also supports proposals and concept studies for new missions to the outer planets. She enjoys yoga and hiking, especially through her favorite park, Yosemite, and is married with 3 daughters and 5 grandchildren. So up first tonight, perhaps one of the coolest grandmothers ever, Dr. Linda Spilker.
Thanks, Mark. That was a great introduction. And as Mark indicated, Cassini has truly rewritten whole textbooks on the Saturn system, from the planet itself to the complex ring system to these just amazing and astonishing moons that come in all shapes and sizes, and then the great magnetic field that surrounds the planet itself. Now, I'm going to cover some of the highlights of Cassini's journey in the Saturn system, her 12-year voyage around Saturn. And then Earl is going to talk about the grand finale, those last precious orbits of Cassini with truly unique science, essentially like a brand new mission, and then those final moments with Cassini. Now, if you look at the picture behind me, this is one of my very favorite montages from Cassini. And as a ring scientist, you can probably guess why. In this, you can see all of the major rings of the Saturn system. And it's a unique geometry. The planet itself is covering up the sun, allowing Cassini's sensitive cameras and detectors to mosaic this backlit view. It's kind of like looking through a dusty windshield or something, and these particles brighten up and you can see them. So what you see is the planet itself, then the main ring system. That faint ring just outside the main ring system is the G ring, and that beautiful blue ring is Saturn's E ring. And it's created by tiny icy particles that come from the south pole of Enceladus that go on to form a ring that fills Enceladus's orbit. These particles even go all the way out to the orbit of Titan, one of the distant moons at Saturn. Now, if you look closely at Saturn, you'll notice that there's a white ring around the planet. And this is where the sunlight is refracted through the top of the atmosphere into your eyes. And it's so beautiful because when you look at this ring around Saturn, you're seeing every sunrise and sunset on the planet at the very same time. And you're looking at the dark side of Saturn, and yet something is lighting up the night side. And what's lighting up the night side is actually light coming from Saturn's rings. So the sunlight hits the rings on one side, and it then reflects onto the night side of Saturn. So just one of the many, many incredible images that have come back from the Cassini mission. Now, I'm often asked, why do we explore space? Why do we send robotic emissaries out like Cassini? What are some of the grand questions we hope to answer? And Cassini addresses two of those. These are something that were in a survey for planetary science. We do these once every 10 years. So the first grand question is, are we alone in the universe? Has life originated somewhere other than Earth, perhaps in our own solar system? And how did life originate on the Earth? Another grand question is, how did the solar system and the Earth within it come to be? How is it evolving, and where is it headed? By studying the planets in our solar system, we can learn about how our solar system formed, how the planets may have migrated as the system evolved, and where we might be headed. And it's a good analogy for other systems around other stars. Now here's and I just want to go back briefly here and show you, these are the 8 planets in our solar system. Saturn is the 6th planet out from the sun. It's the 2nd largest planet, and it takes 30 years to circle the sun a single time. Now Saturn is indeed huge. It's the 2nd largest planet. This shows the Earth and the Moon to scale and the distance in between them. And so you can see that Saturn would just fit in between the Earth and the Moon. And if the Earth were a tiny marble, it would take 764 Earths to fill up the volume of Saturn. So truly a giant planet. And what you're seeing are just cloud tops. Saturn doesn't have a solid surface like the Earth. It's all clouds, mostly hydrogen and helium, and maybe a tiny rocky core about the size of the Earth in the center. Now here's an overview of the Cassini mission. Cassini was launched from the Earth in 1997. We used gravity assist, 2 of Venus, 1 flyby of the Earth, 1 of Jupiter, and arriving at Saturn in July of 2004. Now originally, Cassini was funded for a 4-year prime mission. And by the end of the prime mission, we found we had enough fuel and a healthy spacecraft that we actually had 2 extended missions. The Equinox mission, where the sun was shining right on Saturn's equator, edge onto the rings, and then a 7-year solstice mission. And northern summer solstice at Saturn will be in May of 2017, and the mission will last just past that, ending in September of 2017. And you can see there at the end in the green box what we could call the proximal orbits or grand finale orbits, and they're shown above, highlighted in this box. And this whole mission is shown against the 30-year orbital period for Saturn. So by the end of the Cassini mission, at the end of 13 years, we'll have been in orbit in the Saturn system for almost 2 seasons. They change very, very slowly at Saturn. And right now, Cassini is almost to that green box. We're going up an inclination, and we're getting ready for our final set of orbits. This is another view of the Cassini mission by year. You can look across the top bar, shows the number of orbits and the shapes of those orbits. Then you can see that by the end of the mission, we'll have 127 flybys of the giant moon Titan. And Titan is like a giant rocket engine. Every time we fly by Titan, it's like expending almost as much fuel as we spent to go into orbit for Saturn orbit insertion. And we get great views of this very interesting body as well. We've had 23 flybys of Enceladus, and in the prime mission, the first 4 years, we had 3. We discovered Enceladus was so interesting that it reshaped our thinking for the extended mission, and we added 20 more flybys of Enceladus. We have 15 flybys of the other icy satellites, and then you can see the seasons changing from northern winter to northern summer over the course of the Cassini mission. And then, of course, those proximal or grand finale orbits at the end, and Earl will be talking about those in more detail. This is a Cassini orbiter and the Huygens probe. You can see a great model, a quarter-scale model over in the corner of the Cassini spacecraft. Cassini, she's about 22 feet tall. That antenna at the top is about 13 feet in diameter. It's comparable to the Voyager antenna you can see over in this other spacecraft here. You can see people for reference. And fully fueled, Cassini weighed 6 tons, and about half of that was fuel that we spent about a third of that just to go into orbit around Saturn. The Huygens probe was provided by the European Space Agency, and it was specifically designed with the goal of being thrust into Saturn and Titan's atmosphere, parachuting down and landing on the surface of Titan. Now, Cassini isn't just a spacecraft that's made up of metal and bolts and bits and pieces, but this is kind of my view of Cassini. I see Cassini as made up of all the people that are on her team, the scientists, the engineers, the support staff, and in a way, Cassini represents all of their hopes and dreams, all of the things that we want to accomplish. And there are times when I almost picture myself there with Cassini in the Saturn system as we get back some of these wonderful images or spectra or data of these incredible places. And I almost feel like I'm right there looking through Cassini's eyes and watching as she collects her data, and feel very proud to be a part of this incredible mission. Now on to some of the science. This is the tiny moon Enceladus. Enceladus is only 300 miles across. Enceladus would fit between Los Angeles and San Francisco, so it's a very tiny moon, and yet a very interesting one. When we saw it with Voyager, we saw a very bright, icy surface. Generally in the solar system, something bright means that it's young. You haven't had a chance to build up the pollution from the micrometeoroid bombardment. And also you'll notice as you go south, there are very few craters. In fact, there are no craters at the south pole of Enceladus. And you can see 4 tiger stripe fractures. That's our nickname for those bluish features there. Alexandria, Baghdad, Cairo, and Damascus. So have very interesting names, and those fractures were something that were in darkness when the Voyager spacecraft flew through the Saturn system. So we didn't know they were there until we had the Cassini spacecraft. Now, our first flyby in July of 2005, our magnetometer team said there's something interesting going on with Enceladus. The magnetic field lines from Saturn don't go down to the icy surface like they normally would for a body frozen solid. Instead, it kind of reminds us of a comet. Those field lines are standing off. There's something going on in the southern hemisphere. And so they encouraged us. We had a 1,000-kilometer flyby the first time. They said, go closer. We can really get a lot better data. So we went closer and also trained our other instruments on Enceladus. And we found here, this is with the composite infrared spectrometer, the team that I work with. They found that the Enceladus south pole was hot. It was about 100 degrees hotter than the rest of Enceladus. And if Enceladus were frozen solid, it was much hotter than it should be. And in looking more closely, that heat lined up with those tiger stripe-like fractures. So this excess heat was a puzzle. We had an occultation of a star going behind this region. We looked at these tiger stripes in more detail on the various flybys. Here's a tiger stripe. It's about a mile or so across, typically about 100 miles wide. And it's just this large gash, 4 of them in the South Pole. You can almost see what looks like a frosted side on the left-hand side there. We wondered what could be going on with these tiger stripes. We also had images, and the answer, it was very clear. There are jets of material, water vapor, water ice particles shooting out of these tiger stripe-like fractures. Here's another view of those jets coming out, just going all different directions, continuously going off ever since Cassini arrived at Saturn, and we've been watching Enceladus. So not only do you get water vapor and water ice coming out, you have things like ammonia, methane, carbon dioxide. You have many of the key ingredients that you might need to find life coming out of these jets on Enceladus. And part of the goal of our flybys is actually to fly through this material. And in October, we came within 50 kilometers of Enceladus' surface, right under the South Pole. And it gave us a chance to essentially taste and smell those particles, figure out what they were made of, and try and figure out the activity inside of Enceladus. Here's another view of those icy jets. This is a backlit view, similar to what you saw earlier in the Saturn image. You can see the sunlight shining through each of these jets. And we found in the particles that some of those were salty. There's a global ocean underneath Enceladus' icy crust, and it's as though there were frozen sea spray. And they contain sodium and potassium salts. And we know the pH of the ocean, very similar to the oceans here on the Earth. So very interesting finding in the particle data. This is an interesting view. This is another Enceladus. This is a fountain at Versailles in their gardens there. And this particular Enceladus is a Greek giant, and he had a run-in with his grandniece Athena, and he lost, and so his fate was to be forever buried under Mount Etna. So I think here he's protesting a bit with this giant 82-foot-high geyser of water. Who knew in the 1670s that Enceladus would actually kind of be doing something like this? Now here's an artist's concept of what might be going on. You have the liquid water ocean underneath the icy crust, and that carbon dioxide might be sort of like shaking up a champagne bottle. You pop the cork, and perhaps that's the energy that's there to raise that water vapor and icy particles to send them continuously into space. Now, most of the material falls back onto the surface of Enceladus. The particles are too large, and they fall back, and it's like it's snowing. If you could stand near a tiger stripe underneath it, you could put out your hands, and it would be like it would be snowing on Enceladus. Maybe a future vacation destination, you know, who knows? But some of the tiniest grains escape into space, and they're what go on to form that very beautiful blue E-ring that you saw in the first image. If you look carefully in this image, you can see this tiny black dot. That's Enceladus. Underneath it is the bright plume of material coming out, and you can see wisps and tendrils of those icy particles going out to form the E-ring. Now, the E-ring particles are so tiny that they spread throughout the system, and if you turned off Enceladus's jets, it might only take 100 or 200 years until the E-ring is gone completely. So that's sort of a clue. We see the E-ring, we know the jets are going off at Enceladus. This is just an artist's concept of the inside of Enceladus. We know it's differentiated. That just means it's separated into a rocky core, a global ocean, and an icy crust. We've also found that in looking at some of our particle data, there are tiny grains of silica. We call these nanosilica grains. What's unique about them is these nanosilica grains can only form in water that's near boiling. So what we think happens is that the water goes into the rocky core of Enceladus. It's heated up there. Enceladus is kept warm by a resonance with another moon, Dione, that's essentially just pumping heat energy into it. And once that water is heated up, it absorbs these minerals, in particular silica. When the silica comes back out through these hydrothermal vents, hits the cold water, those minerals condense into tiny particles. Then those particles are frozen into the particles that go out into space that Cassini can measure. So this is an indication that there's a possibility of hydrothermal vents on the seafloor of Enceladus. Now, if we look at our own planet, we have the same kind of hydrothermal vents on the seafloor of the Earth. This is along the mid-oceanic ridge in the Atlantic Ocean. It's very, very deep. No sunlight penetrates to that depth. This is illuminated from basically the headlight of the submarine that's looking at this particular event. And here you have silica and potassium and other minerals that condense in the cold water on the Earth's seafloor, forming what looks like smoke. And these are what is known as white smokers on the Earth. There's also something along the sea, depending on the composition, there are black smokers as well, and they're more iron-rich, so a different composition. What's interesting is here in the deep, cold ocean, where you have no sunlight, the only heat energy and nutrients are what's coming out of these vents. You find an amazing array of life. You find tiny crabs, you find tube worms, you find little tiny animals, all sorts of life in an island around these hydrothermal vents. And so we wonder if we can find life in our own ocean. Perhaps might there be life in the ocean of Enceladus? So some of the factors that life might exist there include a global salty ocean, pH very similar to our own. We know it's long-lived. A global ocean probably formed at the same time as Enceladus. There's organics coming from the ocean to the limits of the instruments we have to detect them. Carbon chains up to C6, C7. They're probably even longer, but that's the cutoff of the instruments, what we can measure. Heat energy coming from the hydrothermal vents on the seafloor. And best of all, for Enceladus, it's giving us free samples. And it turns out when we launched Cassini, we had no idea that there'd be these jets or vents coming out of Enceladus. So we didn't carry the instruments that we would have needed to look for amino acids and fatty acids and long-chain molecules that could tell us that life is there. So this just means that this is a wonderful destination, this ocean world, to go back to Enceladus and to keep exploring and answer the question, are we alone in the universe, or perhaps might there be life in Enceladus's ocean? Now, another very interesting moon is Saturn's moon Titan. Titan is about 10 times bigger than Enceladus. In fact, Titan is about the size of the planet Mercury. If Titan had formed anywhere else in the solar system, Titan would be a planet instead of a moon. Now, this was the Voyager view of Titan, and we just saw this hazy world, and we couldn't see through to the surface. So after the Voyager flybys in the 1980s, a group of scientists got together and said, you know, we really need to start thinking about going back. And it was both US and European scientists, and that was basically the birth of the idea for what became the Cassini mission. Now, Titan has a very dense atmosphere. It's made mostly of nitrogen, very similar to the Earth's atmosphere. No oxygen, but it has methane in its atmosphere. And methane is really the key at Titan, because you see, methane plays the role at Titan that water plays here on the Earth. The methane can be a gas, it can be a liquid, it can form clouds, it can rain onto the surface of Titan, that the temperature of Titan's surface is just right to be at the triple point where you could have a liquid, a solid, or a gas for methane. Now, the methane is also part of the problem with the smog on Titan, because you see some of the methane goes high up in the atmosphere. The solar photons, the UV, breaks the methane apart. They grow into larger and larger chains of molecules, and that forms haze, very similar to the smog that we have here on the Earth. When the particles grow large enough, they actually fall down onto the surface of Titan. Now, the Huygens probe was built specifically to go through the atmosphere, land on the surface, and reveal the surface for the first time. And so this is an artist's concept of the Huygens probe. You can see it coming in. It was released from Cassini on December 25th, 2004, and entered into the atmosphere and landed on Titan on January 15th of 2005. So the heat shield basically ablated away, carrying away the heat energy. And once the probe had slowed down enough, then the parachute could come out. And for the next 2.5 hours, the Huygens probe floated gently down to the surface of Titan, softly landed on the surface, and returned data for another half hour. And Cassini was the relay, so as the Huygens probe was floating down, Cassini was flying overhead, collecting the data, then to send back to the Earth for the Huygens probe. So really an amazing mission. With Huygens, we didn't know what we'd find. Would we land in an ocean, global ocean of methane? That was a possibility. So we built the Huygens probe to float, at least for a few minutes. But it turns out that we didn't have to worry about landing in an ocean. Instead, here's the view that we had with the cameras. We measured not only the pressure, temperature, and composition of Titan's atmosphere on the way down, but the cameras took these pictures. And about 60 kilometers above the surface, the haze finally started to clear, and we got a view of the surface. And we started to see what looked like mountains as we went on our way down. And in fact, the Huygens probe became the very first object to land in the outer solar system, land on a body the furthest away from anything we've had previously. Here's a view of the surface. You can see on the leftmost panel, these are rounded icy pebbles. It tells us that fluid has flowed in this region. Probably we landed in what was the equivalent of a dry lake bed. We had a lamp. You can see the spot for the lamp here to give us an idea of what the color might be of the surface. And you can see the icy pebbles here. And here's a really neat comparison. This is from our own moon. Here's a footprint of one of the Apollo astronauts. You can see the astronaut and the little flag up here. So this is sort of the same perspective view that we had on Titan. And we also could see all of these channels indicating that indeed methane was flowing. And we found a world that was remarkably like the Earth in so many ways. In fact, there were lakes and seas at Titan's North Pole, lakes of methane. In fact, this Lake Ligeia Mare is about 50% larger than Lake Superior. It's about 500 feet deep, which is about the depth of the Great Lakes as well. So there's a tremendous volume of methane on the surface of Titan. And in fact, if you could gather up all of that methane, knowing the depth of this sea is a typical depth, you'd have 10 times more hydrocarbons than all of the reservoirs we have here on the Earth. So if only we could build a pipeline big enough to go from Titan all the way back to the Earth, our problems would be solved. But there's just tremendous amount of hydrocarbons on the surface. And you can see the channels flowing into that particular sea. Dunes, those particles that form high in the atmosphere, fall down, form these long, dark, linear dunes that wrap around the equator of Titan. Those long, dark, linear features. There's also mountains. This is a mountain color-coded with height. Mountains can be as high as 1 kilometer or so on Titan. And we think perhaps in this case, you look at it, it might have even been an ancient cryovolcano. Perhaps water mixed with ammonia flowed out on the surface of Titan. And perhaps with that water, perhaps came the methane. There's not enough methane in Titan's atmosphere to have lasted from the time Titan formed. So there needs to be some internal source periodically releasing methane. Otherwise, once the methane gets divided up in the upper atmosphere, the atmosphere would collapse. So there's some source of that methane. Clouds, we've seen lots of clouds. This is a colorized cloud. We've seen lots of clouds and weather on Titan. We even saw a rainstorm, a methane rainstorm on Titan that darkened the surface, and then we watched with time as the surface slowly dried up. Then here's a view of the dry riverbeds. Now, in looking at these images, what you see here, the lakes and the dunes are taken at radar wavelengths. Radar wavelengths are very good at penetrating through the haze, and so we really have gotten tremendous views of a large portion of Titan's surface. This view is what you would see with the cameras. You can see hints of the lakes in the North Polar region. What we did is we carried near-infrared filters specifically designed to go through and penetrate the haze and look at those. One of the things in the beginning we didn't know for sure is, in those lakes, was that truly a liquid or some kind of a goo or something? What really was it? And we were trying to figure out, how do we find out if it's a liquid without going there, landing in the lake, and finding out? And it turns out we have another instrument, the Visual and Infrared Mapping Spectrometer, looking at near-infrared wavelengths, and at 5 microns it found a bright spot called a specular reflection. If you have sunlight coming in at an angle reflecting off a liquid surface, it comes out at the same angle, and if Cassini is looking at that angle, you'll see a bright spot over the lake. If you've ever been on an airplane, sometimes if you're looking out the afternoon window as you go across a lake or a river, you might notice there's this bright spot that pops up when you go over a liquid, and that's a specular reflection. Now, I just want to say a little bit about the rings. The rings have very simple names, A through G. We keep naming them with other letters as more of the rings are discovered. The main rings of Saturn is off to your left. The main rings that you would see through a telescope are the A ring, the Cassini division, which is the astronomer that discovered Cassini division and for which our mission is named, the B ring, which is the most optically thick ring, and then the C ring. And there are also additional rings just shown in the bottom panel. Here's the innermost D ring. It's very, very faint. You've got the tenuous, very narrow F ring just outside. Then here you have the E ring going all the way out to Titan. And it turns out there's one more ring in the Saturn system. And this ring wasn't discovered by Cassini, but it was discovered by ground-based observers, and it has created by Phoebe. So there's a ring, the Phoebe ring, that actually comes in to the Saturn system as well. Now here's a Cassini view of the rings of Saturn. They're made mostly of water ice, and on average they're only 30 feet thick. So incredibly narrow for the hundreds of thousands of kilometers that they span from end to end. There's tremendous amount of detailed structure there. Some of it we understand is the interactions with the tiny moons just outside. But so much of that structure, we still have no idea what's causing that incredible structure. We do know that there are 2 moons that actually orbit in the rings. There's one that orbits in the Encke gap, named Daphnis, another one named Pan. These 2 moons keep their gaps open. So we know that, that information about the rings. And here's a nice view of the very dark, very, very tenuous D ring. Now this is the lit side of the rings, what you would see through a telescope. But there's also another side to the rings. And this movie was taken by Cassini. Basically, you're riding along as Cassini is plunging down through the ring plane. You can see the A ring, Cassini division, and B ring. Every once in a while, you'll see a tiny moon go by. There's Titan. You can see it's much larger. Now you get to see the other side, the dark side of the rings, the side where the sun isn't shining. In this case, the B ring blocks out all the sunlight. The Cassini division is very bright. The A ring is bright. And you can just see a hint of the bright C ring. So the rings look very different. And that's the advantage. If you go to a place like Saturn, you can see the rings on both their lit and their unlit sides. Now, Cassini also had a rare opportunity at equinox. In fact, we just had our autumn equinox, just I think very early this morning. And that's when the sun shines directly on the equator. And in this case, it shines on the rings edge on. And that's important because with the sun edge on to the rings, essentially you've turned the sunlight off for the rings. And this mosaic taken by Cassini, what we've had to do here is increase the brightness of the rings by about a factor of 20. So you could even see them because they're only now illuminated by Saturn shine. And around on the dark side of the rings, where it's dark before Saturn's shadow, we've had to increase the contrast by about a factor of 60. Now here you can see the narrow F ring, but it's slightly tilted. So it can still catch the sunlight even around equinox. Now with 30-foot thick rings, what's unique is you can look for anything that sticks up above or below the ring. So if you're bigger than 30 feet in size, there's a chance you'll cast a shadow and we can see you. So we're looking for objects with Cassini that would be larger and would cast shadows. And so I'm just going to show you an image now. This is the outer edge of this ring, the B ring, and it's stretched out. And lo and behold, we found shadows, lots of them. Turns out that the outer edge of the B ring is held in place by a resonance with one of Saturn's moons. And it looks like some of the largest particles, or maybe they form and grow right there at the edge of the B ring. Now, some of these are probably a kilometer or two in size, casting very long shadows, but there are hundreds of them across the B ring, almost looking like little mountains along the B ring. And a good analogy is if you wanted to, say, find the pyramids, if you're looking out from the space station, if you looked around noon, they'd be hard to see against their sandy background. But if you looked near dawn or dusk, the equivalent of equinox, they would cast long shadows, making them much easier to pick out against the sandy background. So in the same way, Cassini used this to look for structures, and we found a number of different structures like this that would cast shadows in the ring. So as a ring scientist, a very exciting time to be looking at Saturn's rings. And finally, here's a very interesting discovery for the rings. It turns out that there is a feature. This feature is about 1,200 kilometers long, 10 kilometers or so wide, indicating that there's a tiny object 2 or 3 kilometers in size creating this feature. This feature is right at the edge of the A ring. So it was discovered in 2013. Its discoverer, Carl Murray, discovered it on his mother-in-law's birthday, so he nicknamed it Peggy after her. So this tiny object that's here creating this feature, Peggy, we've been watching for her ever since. She comes and goes. We're wondering, will she break free of the rings and become a moon in her own right? Or will she be torn apart and jostled by the other particles in the rings and disappear? So far she's still there. We're going to keep watching for her through the end of the Cassini mission. We're kind of rooting for her by now because she's been around for a few years. Moving on to Saturn, one very interesting event happened at Saturn. A giant storm developed toward the end of 2010. This storm grew so huge, it was a giant vortex, and that vortex swirled off this huge tail. The tail of the storm wrapped itself around the planet. There was another vortex on the other end, kind of like a hurricane. When these two vortices merged, that marked the end of the storm. A tremendous amount of energy was released in this storm at Saturn, and typically these storms happen about once every 30 years. And so this was the 5th time we've seen a giant storm like this at Saturn. But what was unique is this storm was early. It had only been 20 years since the last storm, and so it came early so Cassini could get a good view of it and watch it. And so we watched it, as did ground-based observers. It lasted about 9 months and started to fade. Now this is in the visible. If you look toward the near infrared, you see deeper into the atmosphere. The colors in this view, if it's white or yellow, that's high up in the atmosphere. Green is also high up. That's the center of the storm. And then the oranges and the reds are looking deeper. So we're basically getting a profile of what that storm looked like and how those clouds behaved. And we can model that and perhaps use it as an analogy to storms in the Earth's atmosphere. Now looking at some of the longest infrared wavelengths, the thermal infrared, turns out that the storm was in the lower atmosphere of Saturn, the troposphere. But when those two spots merged, it released a tremendous amount of energy, kind of like a giant burp. And here up in the stratosphere is a large, very hot feature. And this feature persisted for a couple of years and has slowly cooled. So a very dynamic and active Saturn at least in that time period. Now, Saturn has a very interesting feature at its north pole. Here's that feature. You're looking right down at the north pole of Saturn. That feature is a six-sided jet stream called the hexagon. The Voyager spacecraft first saw this feature in the 1980s, and it was still here when Cassini arrived. You can see the pinkish clouds. This is a false color view rotating around, and they go faster the closer you get directly to the North Pole. And at the North Pole, there's a giant hurricane. And this hurricane is about 50 times larger than a typical Earth hurricane, blowing about 340 miles an hour. And finally, before I pass it over to Earl, this is a view of the changing seasons. In fact, Saturn's shadow on the rings you can think of as a giant sundial. And this picture taken back in April of 2016, you can see that the shadow of Saturn goes out just past the Cassini division. At solstice, that shadow will pull in until it's about in the middle of the B ring. And so as that shadow pulls in, so will Cassini's time shorten at Saturn. With that, I'd like to turn it over to Earl to talk about the grand finale.
So how does Cassini follow that? How do I follow that? I want to go first next time. You know, one of the things about Cassini is it always trumps itself. You know, as we keep finding, you know, one year we announce a subsurface ocean, next year we announce a global ocean. So it keeps building and building and building. And then you look at the last 12 years, and how do we do something even more spectacular in our final year? Well, I'm going to show you at least the potential for that. But before we do that, I want to just a little bit of a backup here. I want to go to the end. This is September 14th, 2017. It's about 2 o'clock in the afternoon here in Pasadena. And Cassini has just wrapped up a 30-hour or so observing session. The recorders are packed full of images and data, fields and particles data. And so now it's time for Cassini to turn back to Earth and begin to play those back. So this is a high-speed, slow-speed version of the last of these periods. So Cassini's going to be working on this for about 10 hours. The DSN is going to be receiving all this data. We are going to be streaming these back, and as soon as we see them, you'll see them. Some spectacular images of the poles and of the rings as we come in. And then when the SSRs, the solid-state recorders, are empty, it'll be about 10 hours. Cassini's going to reconfigure for the periapsis here at Saturn. I want to make sure So we've done that 292 times over the last 7 years. Periapsis at Saturn is pretty routine, but not this one. This one is absolutely unique because it's Cassini's last. 3 days before this event, Cassini had a close encounter with Titan. Titan gave it a little gravitational nudge, and that nudge has pretty much sealed Cassini's fate. As a matter of fact, it's not coming out of this periapsis. It's moved the periapsis, the closest approach distance, inside the capture radius of the Saturn's atmosphere. And so Cassini, this one, is going to reconfigure itself so that it doesn't put the data on the recorders. It's going to put everything out on the pipe as quick as it can. So the minute you see, now it's going to start to turn colors here as Cassini reconfigures. Cassini is going to go into the atmosphere, and every second of this data is going to be coming back to the Earth. And unfortunately, Cassini is going to be going 77,000 miles per hour. You can get around the Earth in about 20 minutes at that speed. So what's going to happen? It's going to happen very, very fast. We are going to have every piece of data streaming back down. We're going to be sampling the atmosphere and trying to answer some of the fundamental questions about Saturn's atmosphere. But it's not going to be very fast, not going to be very long. At 77,000 miles per hour, Cassini is going to be going in with its antenna pointing to the Earth, but the atmosphere is going to quickly overpower its ability to point. It just doesn't have that kind of control. It's going to push it off, and then we'll lose comm. It will essentially disappear from our monitors, and about 3 or 4 minutes later, that speed and the density of Saturn's atmosphere will vaporize Cassini, and it is over. One of the most spectacular missions ever to leave Earth, a discovery machine like you will never see, and it's going to be done. So Why are you doing that? I mean, the first thing, did you guys ask anybody's permission to take something that is rewritten, science programs, redirected NASA programs, and recontoured missions? You're just going to destroy it? Let me give you I'll try to explain why we think that's a good idea. In order to do that, I got to go back a little ways. So back to 2009. Linda told you about the prime mission and the extended missions. We got to Saturn in 2004, right? We had a 4-year mission, but we didn't have any end. There was no end game planned. But we got to the end of that mission, realized we had an incredibly good spacecraft, lots of propellant, so we went for another 2 years. About midway through that second mission, 2009, we said, geez, all subsystems are great. This system is wonderful. We've got a lot of gas in the tank. Let's do something else. So what? What's next? And we actually got a lot of studies done. You know, there's a lot of opportunities at this point with all the subsystems going. We could have left Saturn. We could have gone off to the Centaur asteroids and turned ourselves into, reconfigured, repurposed Cassini as an asteroid mission. We could have, believe it or not, left Saturn and gone to Jupiter, or gone out to Uranus, or gone out to Neptune. Now, I gotta say, this was a 40-year cruise, so, you know, I mean, it would have been a long cruise, but, you know, look where Voyager is. It was possible. We could have gone back to Jupiter. That actually is an image we took on our way out, and we could have gone back and spent, you know, the same set of resources on Jupiter we did on Saturn. Uranus is also a possibility, or more of Saturn. Well, you know, this is kind of a no-brainer. I mean, we had barely scratched the surface. Saturn is just incredible. You couldn't have asked for a more dynamic environment. You've got the rings, you've got the planet, you've got the icy satellites, you've got Titan and Enceladus, little prebiotic worlds on their own. And Cassini's still unwrapping this. So it's really not hard to figure, okay, we got to stay. So, you know, I'll jump to the chase real quick. Nah, we're not going there. Nah, we're not going there. We're going to stay. But there's a catch. If you want to stay at Saturn, there's some rules. And they are, we call it planetary protection, but the real essence of this is you've got to protect Saturn's ocean worlds. Cassini is essentially a victim of her own discoveries. My apologies to the Oak Ridge boys, but you can visit, but you can't stay. So you've got to make sure that if you stay in the Saturn system, there is no possibility of a crash landing on Enceladus or Titan. Cassini is room temperature inside. If there are little microbes in there that don't mind a vacuum, they could last forever. We were running essentially at about 72 degrees inside the spacecraft, and so going and taking some of our Earth microbes or spores onto Enceladus in particular, where we know there's water, warm water, would just be absolutely unacceptable. So you guys can stay, but you got to be careful about what you do about Titan and Enceladus. So with that in mind, you say, well, how are we going to do that? We could stay and do big, long orbits, you know, stay way outside the orbits of Enceladus, way outside the orbits of Titan, but guess where all the science is? It's down there with Titan and Enceladus. So we want to explore these guys, but we want at the same time remain safe. So we go to the trajectory designers. We got a fair bit of propellant. We got good subsystems. What can you guys do for us? We want to be able to stay inside Saturn's system. We want to explore all the icy satellites. We want to explore the rings of Saturn, but we want to still remain safe for these two, you know, incredible worlds. So what these guys gave us was the Solstice mission trajectory. This started in 2010, and this is a trajectory designer's masterpiece. It's a lot of squiggly lines, but each of those is an orbit. And every time that orbit changes shape, it's because Titan moved us. As Linda said, we get essentially a Saturn orbit insertion velocity change every time we fly by Titan. So you want to go up, you fly under Titan, and it pulls you up. You want to go in, you go to the right, go to the left. And we take you all over the system. So what we did, what the trajectory designers did, they took these orbits, we stayed very flat in Saturn's plane. That's, by the way, that's Saturn there in the middle. Very flat, and then you could stay and do all the satellite interrogation you want. You could go very inclined, very looping orbits to do magnetic fields and to do the poles and the rings. And as a bonus to all of that, this is the first 6 years of this mission, the mission that Linda just reported. You also get this. This is the last year of the mission. And this is, unfortunately, at the end, the demise of Cassini, as I described just a few moments ago. But on the way in, we have an entirely new mission, something we have never done before. We're going to flirt with the outsides of the rings, and then we're going to go diving deep in between Saturn and the rings. And I'll show you a little bit more about that just to show off some here, because these things are just phenomenal. The key orbital characteristics of this final set of orbits, which we call the F-ring and proximals, you'll hear some of the flight team call them FERPO, which sounds more like a dog food than a real acronym, but really they're the F-ring orbits and what we're now calling the grand finale. 42 short period orbits. Each of these orbits lasts about a week. The flight team is going to be running around like you've never seen. 20 of them are going to be, oops, I've hit the wrong button, sorry. I hit it again. There we go. 20 of them are going to be just outside the F ring, right? This is the outermost ring here. Titan is going to be, and both of these essentially run into Titan right out here. 20 of these outside with great coverage of the poles and the rings, and then another Titan flyby is going to move us in to the gap between the innermost D ring and the outermost edges of Saturn's atmosphere. 22 of those. The periapsis is going to be in what we call a 2,400 kilometer clear zone between essentially Scylla and Charybdis. We've got the dust on the left and we've got the Saturn on the right. We've got to navigate in between. Next slide is, I think, a look at the view from Earth. Not only are these things phenomenal from their proximity to the system, the geometry is also phenomenal, because if you look at what happens here, these orbits go behind the rings and behind Saturn. Almost every one of them, from a view from Earth, provides what we call occultation. Not only do we have instruments that can photograph and sample, we also have instruments that can send a very, very precisely tuned radio signal to Earth. And passing that signal through the rings and the atmosphere can tell us a tremendous amount about their internal structure. The opportunities here are absolutely phenomenal. And we, by the way, Saturn is obliged by never, if you recall back to Linda's picture, never opening up the rings more than they are right now. So essentially be passing these waves right through. It's an absolutely unique and spectacular opportunity. This again is just to show a little bit of what happens at the periapses. You can see, you don't quite see the F ring on this illustration, but it is right. Oops, I've done it again. There we go. We have these rings here. The F ring is actually coming out right here. We have about an 8,000 kilometer gap there, but there's extended dust. And if you look at the F ring, I'm actually more terrified about that than I am about the gap, because of these tendrils that keep coming off the F ring. But nevertheless, that's where we're going. And then, again, you see the proximity of these periapses here inside for what we call the proximals, the grand finale. This is, again, just kind of showing off, but here is a flattened out version. These are the rings of Saturn. Here's the F ring up here, and here is Saturn's atmosphere down here. Atmosphere. Saturn doesn't have a surface, or if it does, it's way down in there. So what we call the surface is essentially the one bar level, essentially the pressure at sea level. So that's what we're calling the surface of Saturn. So here are graphically each of our periapses. So we're flirting around in this safe little gap between the F ring dust. I've done it again. We'll get to that. Between the rings here, incredibly precise navigation to stay between the dust hazards, between the F ring and the Janus and Epimetheus rings here. Then the Titan flyby that brings us down in here, and then we stay very carefully and very precisely within the gap between Saturn's atmosphere and the dust until our final flyby here. Now, I should point out there are a couple that are actually flirting with this, and we're going to do some things here to keep ourselves safe, because they're a little bit more dicey than the others. Okay, so what's it like to be on Cassini when we're doing this? already stolen my thunder on this slide a couple of times. Imagine you're just sitting on the prow of Cassini going through. This is 7 seconds of terror every 7 days for 7 plus 2 months. So Mars has got their 7 minutes, we got 7 seconds every 7 weeks. And this is the white knuckle time for us. Now we won't know, because most of the time going through here, we don't want to have the spacecraft talking to us. We want it to be doing science. So we'll find out if we've survived these ring plane crossings much later in the game, but that's the way it goes. You want to get the science, you don't want to find out if you're going to make it. So this is going to happen 22 times every Tuesday, I believe, but I could be wrong about that. And so the flight team, there are many of them here, we are going to be very, very busy. So the science. I love the engineering of all of this, but really the engineering is all in it because of the science. And this is just some of the unique things. You've seen what Linda showed already, and it is phenomenal, and we're going to continue to do some more of that even while we're here. But these are opportunities that we will never, ever get any other time. Saturn internal structure, magnetic fields, and gravity. We'll actually be able to determine for the first time the mass of the rings. By flying in between the rings in Saturn, we can get a sense of where which one's which. And that tells us something very fundamental. Believe it or not, we don't know how old the rings are. They could be a couple 100 million years, they could be 1 billion years. There's a big argument about that, and very, very intelligent people on both sides of the case. We think we can help with some of these measurements. Saturn's atmosphere and the innermost ring particles, and the highest resolution ever ring observations themselves. When we went into orbit in 2004, we went over the rings, but they were not lit. We got the dark side. So now we can finally see these rings fully illuminated by the sun. And as I showed in that picture earlier, Saturn's cooperating by providing an incredibly good phase angle with the sun. And also, we're going to radar the rings. You saw the radar images of Titan. We're going to try to do the same thing with rings. Polar observations and aurora of Saturn. And then finally, as I mentioned in my first slide, we are actually going to sample Saturn's atmosphere. Every ounce of Cassini's last efforts will be made in sampling the atmosphere and trying to understand and answer some of the fundamental issues about the constituents of the hydrogen-helium ratios and things like that. So we'll see. Let me just quickly run through this. November 30th, right after Thanksgiving, this whole thing starts. And this is just to show you that not only, sometimes you're good and sometimes you're lucky. The longitudinal coverage of the F-rings is absolutely phenomenal. We're going to get the whole planet covered with the F-ring timeline, 20 orbits. April 22nd is our first targeted flyby. This was last targeted flyby, and this is the one from Titan that's going to push us in. So I'm going to try to not hit the go button and show you. Titan's going to come in from over here. Here's the F-ring, final F-ring orbit. We're going to come out back around, and then here comes Titan, and watch what happens to this orbit. Boom. It does. It's about a couple of thousand kilometers, so it's pretty close. But now, rather than going outside, in we go. And that's going to happen for 22 times. Boom. And so there's that, and I won't show you 22 more. April 23rd, the grand finale begins, and we have a lot of Titan flybys pushing us around. I won't show you a whole lot of those. But the first dive through the gap, and here's our longitudinal coverage with the proximals. Again, it's almost a perfect grid all the way around the planet. Absolutely phenomenal. First dive through the gap was on April 26th, and then September 11th, our last flyby of Titan. And I mentioned that before. We call it T292. It's a distant flyby, about 100,000 kilometers, but it doesn't take much to push us in to an impacting trajectory. And September 15, boom, we're in. The end of mission and the end of a very spectacular set of investigations at Saturn. So I want to share a cartoon with you that we at the flight team like to pass around. Hey, Cassini, I hear you're retiring. How about that? Congrats. Do you want to celebrate? Maybe lunch with me and my moons. How about that? Nah, I'm just going to go barreling straight into your atmosphere. learning as much as I can before I'm crushed to death and vaporized in a spectacular whirling inferno beneath your mysterious stormy clouds. So you can imagine Saturn's reaction to that. It's the same, it's the same one that we all have. Maybe you all have when you see that we're going to burn this thing up. You think about that for a little bit, and hopefully what I've just told you, you might come to agree with all of us that it's too bad. It was a wonderful machine. It's been an incredible discovery machine, but it's awesome. But, okay, I think we'll be happy to entertain any questions you might have. And if you do have a question, we appreciate you going up to the microphone.
Thank you for a really awesome presentation. So I believe that the Juno mission is using highly elliptical orbits to explore the internal structure of Jupiter. And I assume you mentioned that you're going to be probing the magnetic and gravitational fields of Saturn. So my question is, at Jupiter, they expect to confirm the existence of metallic hydrogen inside of Jupiter. Is Saturn have enough gravitational pressure to form metallic hydrogen, do you believe?
Yes, Saturn certainly has enough pressure inside to form metallic hydrogen. We're wondering if we can maybe also detect that boundary inside of Saturn. Just want to point out one difference between Juno and Cassini. Juno is in a polar orbit, basically going over the poles. Cassini, we're only tipped at 63 degrees. And that's basically our optimum orbit to keep the periaps from precessing and putting us prematurely into the ring. So very similar complementary science for the two missions, probing the interiors of two gas giants and then comparing the results.
Thank you.
Thank you for the great presentation. I wanted to ask about contingencies during this final year. You're on a risky pathway, and if something were to happen to the spacecraft on one of these passes through the rings, what do you expect to become of the rest of the mission? Is there a chance that it can still have its crash into Saturn, or what?
Yeah. One of the things that's pretty amazing about this trajectory is once we've flown by that final Titan flyby, if we lose the spacecraft, it's still going in. And as a matter of fact, after T125, we require, which is the penultimate Titan flyby, and very minimal trajectory maintenance. We're essentially on a ballistic trajectory to our entry. Now, that being said, we're still going to try to, we've worked contingencies in case we find the dust is higher than we want. We can hide behind the high gain antenna. If the atmosphere is thicker than we would like, although some of the scientists think that's just great, we can move ourselves out a little bit. So we have worked a lot of contingency plans to make sure the mission is as successful as possible. But if we are damaged, we'll be able to keep our promise to Enceladus and Titan.
In fact, if the atmosphere shrinks, and that's a possibility, we also have a plan. We could go a little bit lower because we want to dip our toe for sure in that atmosphere of Saturn.
Hi. This is more of a question about the capability of the spacecraft. So I understand that the decision to deorbit it is quite final. But would it ever have been possible to attempt is there sufficient delta V in the tanks to attempt a rocky or icy moon, like smaller moon landing, like a janky near style, landing, and use the low gain antenna, send another spacecraft later, and have a passive station sitting in orbit around Saturn?
No,
would there be any value?
I'm afraid, well, that could have been, in that set of scenarios, there may have been a landing scenario that we didn't work, but now there absolutely is not. When we designed the Solstice mission, we designed it, you don't want to end a mission with a full tank. In fact, you want to end the mission with a completely empty tank, and right now we are almost completely empty. So the possibility of a controlled landing on anything would be absolutely out of the question. Again, those sort of things, most of the controlled landings that we see are really more like controlled crashes. They're low-speed crashes, and so really the realistic opportunity to create a beacon, I think you want to design something like Huygens that actually was built to broadcast up, but unfortunately it was on batteries, and that was that. But now it's, like you said, the decision's made, and we have spent all our propellant doing what we've been doing. Thanks for the question.
Thank you both for that presentation. It's excellent. You noted earlier you're concerned over contaminating the environments of Enceladus and Titan. How were you able to prevent that when you landed Huygens probe on the surface of Titan?
Good question.
Excellent question.
I think the key difference between those is that Cassini is powered by these radioisotope thermoelectric generators with plutonium on board. And so to access the ocean on Enceladus, you'd probably have to melt through some ice. And with the heat from that plutonium, that might be a possibility. The Huygens probe had batteries and it had some small RHU heaters. And also, when we landed on Titan, we didn't know about the methane lakes. We didn't know that Titan also had a global ocean. We didn't know about Enceladus. So a lot of things, like as Earl said, Cassini is kind of a victim of her own discoveries.
I see. Thank you.
Well, absolutely superb presentations, of course. A quick question. What's the cause of the highlights that we see here at 12 o'clock and 6 o'clock on the outermost rings?
Excellent question. What is the cause of those bright spots? It turns out that those spots are actually, you can think of somewhat pulled in closer to the sun, and so it's sort of a phase angle effect. If you can think of it that way, the ANSA are further away from the sun than the points at the north and the south, and so they are brighter. As many things brighten as you get toward that very low phase angle where that distance between the sun and your target is small. Good question, though. Good catch.
To start, thank you for a wonderful presentation. I've really enjoyed it. Knowing what we know now about Saturn, what's next, and when do we get to go?
It's yours.
Well, there's a proposal cycle underway now within NASA called New Frontiers. And there's a fixed list of missions for New Frontiers. One of those is a Saturn probe. Much as we had a probe into Galileo's atmosphere, we'd like to send a probe into Saturn's atmosphere, in particular to measure the Nobel gases that you can't really measure any other way. And there are a host of other things you could do with the probe. There are also now 2 targets that were added to the list for New Frontiers. Those targets are Enceladus and Titan, basically these new ocean worlds unveiled by Cassini. And so there are missions to go to fly through the plumes of Enceladus with more capable instruments to perhaps look for those amino and fatty acids, missions to maybe land something in one of those seas on Titan and make measurements there. So there's a whole host of proposals. There's probably 30 or 40, or who knows how many NASA will get sometime next spring, and then they'll get to pick one of those missions. So we might go back as early, but it still is a long trip. You're talking about maybe a launch in the mid-2020s, 25, 26, and then maybe a decade or so to get back to Saturn. It's not a quick trip to get there.
I can't wait. Thank you.
And don't forget Uranus and Neptune. I mean, they're out there too, and it would be great to send a flagship mission like Cassini on out to one of the ice giants, Uranus or Neptune. We've just had tantalizing glimpses with Voyager, and to go back to one of those places for a future flagship, maybe after Europa, maybe a flagship to Uranus or Neptune.
Thank you so much.
I'll jump in for one more question. How long does it take for an image to get from Cassini to Earth, like to get the data here? And my iPhone, I think, has 8 megapixels. What's Cassini have?
1 megapixel.
1.
And it's black and white.
Okay.
We colorize our images with filters. And it takes anywhere from an hour to 90 minutes for the image to get from Cassini here to the Earth.
Whole megapixel image to.
Well, the megapixel, let's see. We do 140 kilobits per second.
Okay.
So it takes 10 seconds or so, roughly. Let's say 20, counting overhead, to get an image down here once it starts. But Saturn is an hour and a half light time away. So when Cassini starts to send a signal, her bits don't get to the ground for an hour and a half
For an
later.
hour and a half.
Yeah.
Gotcha.
And so when we want to signal, send something to Cassini and have it answer, we have to wait anywhere from 2 to 3 hours. Yeah.
Wow. That was really great. Thank you.
It just means Cassini has to be very smart. She has to basically have commands on board to keep her going, typically for 10 weeks at a time. Where to point, where to look, when to send data back. And so very, very smart spacecraft.
Actually, speaking of photos, I was wondering what the plan for in the grand finale photo-wise, like, and what are you expecting to see? If you're expecting to take photos, are you expecting to see maybe some resolving some individual clumps of ice in the rings since you're going so close, or looking at the clouds of Saturn because the periapsis is going to be so close? Are you guys expecting to take a lot of photos from this mission?
Well, we'll be taking a lot of photos of both the rings and the planet. Ring particles on average are millimeters to centimeters in size. Even if they were tens of meters, we still couldn't resolve an individual ring particle. But we certainly could resolve the structure that we see in the rings at much higher resolution. SOI, as Earl said, is on the dark side of the rings. This is a chance to look at that resolution, but on the lighted side of the rings. Radar of the rings as well. Also, we'll get close-up views of the planet, of the poles, of the atmosphere itself. I think that the surprises might be the questions we don't yet know to ask. When we look at those pictures, whether it's the rings or the planet, what might we see? Also, we have a detector that some of those tiny ring particles from the main rings charge up, and the field lines then will go into one of our sensors, the cosmic dust analyzer, and we'll get for the first time the direct composition of the rings. We know they're water ice, but we don't know if the non-icy component is silicates, iron, tholins. We don't know what it is. So we'll get the answers for that for sure for the first time.
I might also add that as we enter the atmosphere, everything is going to be focused on atmospheric construction and constituents. The spectrometers, the fields and particles, they'll be pointing at the atmosphere. Unfortunately, that means the camera is going to be pointing someplace else. And furthermore, in order to play all that data back as fast as we can, we have had to narrow down the bandwidth. And a megapixel is a megapixel. We could get 10 or 20 mass spectrometer packets down for one image. So the camera's not even going to be recorded and sent down during those final seconds.
Thank you.
You said in response to an earlier question that you're getting pictures in black and white and then you're coloring them with filters. How does that work? Are you choosing, or do you know what filter colors to use?
Our cameras have 2 filter wheels. Essentially you can take a green, blue, and magenta filter, not magenta, blue, green, well, whatever the 3 colors you pick, and colorize them, right? It has infrared filters that penetrate the haze. And so each of these filter wheels, you actually rotate that filter into the image path and take an image, then rotate another filter, take another image, and they're combined and colorized on the ground.
So the colors you end up with represent what you're actually looking at, or is it?
They can, or they can represent some of the false colors that you've seen, like the red hurricanes and things like that, that accentuate levels of elevation or of chemical constituents.
Okay.
A lot of the pictures you've seen were natural, but some of the others were false colored to highlight whatever meteorological or chemical item you're trying to look at.
But you can get true color. You take those filters and add them together in different ways, and you get the true color that you would see with your eyes in those pictures.
Thank you.
Hi, thank you for your presentations. I have 2 questions here I want to ask. First is that you guys said that the Cassini satellite, the Cassini drones, props, whatever, is the farthest from the solar system we have ever gone. Is it?
Oh no.
No. Well, what I said was that the Huygens probe landing on the surface of Titan is the furthest we've landed a probe on the surface. But the furthest spacecraft now away from the sun would be the Voyager spacecraft. They're well past the orbits of Neptune, Pluto. They're on out, even one of them into the interstellar wind. So
our 90-minute light time, they're a day and a half for a signal to get from the probe to Earth. So they're way out there.
I see. And the other question I have is that if I remember correctly, Saturn has 5 big moons, correct? And so why do you only land on two of those moons?
Well, Titan is the very biggest moon, and it's the only moon in our solar system with a thick atmosphere. And it was the one that had the most questions and puzzles about it. So we really had the weight, on Cassini to carry just a single probe. And so it was easiest to land on Titan. You could land with a parachute. You didn't need rockets or anything fancy. And we wanted to see what that surface looked like. So if we go back, we could carry probes that could land on multiple moons and look at those as well.
Oh, okay. So you mean that you choose the moons you want to land before? Or
Right. We chose Titan. Before Cassini even launched, we had chosen Titan.
Oh, okay. I see. Thank you.
Thank you for the very amazing talk. I had a question on a radio occultation. For the 3 different frequency centers that you have available in the spacecraft, can you characterize a little bit on ring particles that are smaller than the shortest wavelength and larger than the longer wavelengths, and the diffraction patterns and how we would be able to ascertain the particle population?
Right, the 3 wavelengths of the radio science are very diagnostic in helping us understand the particle size distribution of the ring particles. And what we found in looking at those is they're pretty much seeing all of the particles that in that particular size range for that. So they do a good job at Ka, X-band, and S-band in looking through the rings. And sometimes the S-band signal is blocked out first because the rings are so optically thick.
And how does the diffraction or dispersion occur on particles that are outside those wavelength correlations?
Well, the radio science actually has a fairly large field of view, and so it's integrated particles all the way across that field of view. And sometimes we see diffraction patterns that tell us that the ring particles are lining up and are structured in a certain way, forming these things we call self-gravity wakes. We can actually do some work to detect those in radio science as well. If you want more detailed answers, I can give those if you want to come up afterwards.
Thank you.
So this is more of an engineering than a science question, but for all these precise orbital maneuvers, how do you know your position accurately enough to perform these maneuvers?
Ooh, that's a good one.
Because you can't exactly open Google Maps and get your GPS, right?
I got to brag a little bit because JPL is the absolute center of excellence for navigation. What we do, a couple of different things. First of all, we track the spacecraft very carefully. We use Doppler and ranging to measure its velocity and distance very precisely. We fit that to an orbit. At the same time, we're solving for all the ephemerides, essentially the positional points of all the satellites and Saturn. And that's a daily process. As a matter of fact, we're going to do a very tiny OTM tonight, orbit trim maneuver tonight, based on latest observations, because we move, we're moving a kilometer or maybe a few hundred meters, just being pushed around by our own shenanigans as well as smaller forces. And so we're constantly tracking the spacecraft. And over the decades, we've hit comets. I got to say that the navigation at Saturn is one of the triumphs of modern interplanetary navigation because of the precision that we're able to do this. You could do the same thing with much coarser measurements, but you'd have to be carrying tremendous amounts of propellant because every time you miss, you got to fix it to get back on track. So I'd be happy to share a paper with you or two. We've got a lot of papers about this.
And one of the comments was the navigation is so good, it's allowed us to go closer and closer and closer to these targets until we came within just 50 kilometers of the south pole of Enceladus. And in fact, our closest flyby was 25 kilometers, but it just wasn't under the pole. So we have just gotten so good we can go close, know where we're going to hit, and we don't miss.
Thanks.
I have some online questions here. Just want to go through a couple of those. A question from Titan82 wants to know, what is the temperature of the subsurface ocean of Enceladus? Well, if it's true that we have hydrothermal vents, it might be as high as close to boiling point around those subsurface vents. But clearly, if the water is a liquid, even though it's under a little bit of pressure and perhaps with some ammonia, it must be very close, it must be above the freezing point of water. So we know that otherwise the ocean wouldn't be a liquid. The next question is, will Cassini be able to photograph the vertical ring structures as it passes through the ring plane? That's a great question. Unfortunately, the answer is no. We can't photograph these vertical structures very well because they aren't very, very big. We don't think we'll have the resolution to resolve something that's a kilometer or less. And we don't think there's vertical structure in the C ring and D ring where we'll get the very closest to the ring. So I'm sure we'll be looking, and in fact we have looked as we've gone through the ring plane crossings. I don't think we'll have the resolution to be able to do that. And then the sun, if we really want to look for shadows, which is a really great way to look for structure, during this point in the mission there'll be no shadows cast by the ring particles. We're not at equinox, so. Okay, are there any other questions? Okay, if not, thank you very much.
Thank you very much.